All right, guys, Mr. Reynolds here, and it gives a chance to go over some of the worked examples inside section 12.1. This is going to include both wave functions and looking at Heisenberg uncertainty principle and some other things. So here we have a nice little graph. They've been really nice, and they have even given us the wave function squared, which of course the probability is proportional to the square of the wave function, which is helpful. And they've asked us state where the electron is most likely to be found, explain whether the electron could be found either in the nucleus or at the positions corresponding to the largest value of R found on the graph. So the nucleus, of course, is going to be at position 0. And of course, you're not going to be able to find the electron in the nucleus because the wave function is 0. 0 wave function, 0 probability of finding the electron there. At R, you could find the electron out at R. It's very low. It's not gone to 0. The electron could be there. It is just exceedingly rare. Of course, we're going to find that the electron is most likely going to be at A. That is the position of highest probability. Of course, they give you a good explanation here in the solution. Moving on, they talk about the Heisenberg uncertainty principle, give you the equation, all this stuff. I hope you read all this. It's a good little book. Good question here. So the diagrams show the variation of distance x with a wave function psi of 4 different electrons. Scale on the horizontal axis in all 4 diagrams is the same, so we can compare the different graphs, which is nice. It says for which electron is the uncertainty of the momentum the largest. Now, it's asking for uncertainty and momentum. You might be tempted to think it's saying the greatest uncertainty in position. The greatest uncertainty in position certainly is going to be A, because really the electron has a fair shot to be anywhere from here to here. And so I really don't know where the electron is in A. C, I know it pretty well. It's going to be somewhere in this realm right here, most likely. D, it's a little bit wider of a gap. And B, it's probably going to be closer, but again, it really could be anywhere. But they're not asking what's the uncertainty of position. They're asking what the uncertainty of momentum is, which has the largest uncertainty of momentum. So I'm going to use my equation, delta x, delta p is greater than or equal to h over 4 pi. We're looking for uncertainty momentum, and so we're going to say delta p is, we'll just go ahead and say, well, actually, we don't really need that, honestly. We can look and just tell that if we want a big delta p, considering that all the stuff on the right here is a constant, then I need a small delta x. I need the graph that I know the position of the electron the best. And which one is that? Of course, it is C. C has the wave function the most scrunched up. It's the least amount of horizontal spread. D is probably next. Then B, D and B may sort of fight for the next one. A, of course, has the largest uncertainty of position, but the smallest uncertainty of momentum. Okay, we keep moving down. Don't worry too much about this section, pair production annihilation. This, by the way, this is a Feynman diagram. We're going to talk about those next week. So yeah, don't worry about any of that stuff really for right now. Here's that equation. I can't think of the number of times you've really used that equation, to be honest, but there you go. Talks a little bit about quantum tunneling, which we talked about in the last video. Sort of neat little idea. Talk about DNA and stuff like that. And then we get to a good worked example problem. It gives us a gap here, and it has us figure out a couple things. So first, what is a wave function? You see the definition up here. I don't need to read that for you. But B, find the momentum and the uncertainty of the momentum of the electron. So you're really doing 2 separate things in this case. First, to find momentum, we're going to use the de Broglie wavelength equation. Wavelength equals h over p. Solving for p, p is h over the wavelength. And I can tell the wavelength in this graph because I can see there's, let's count them, there's 1, 2, 3, 4, 5, 6 complete waves within this 2 times 10 to the negative 10th space. So the wavelength must equal 2 times 10 to the negative 10th meters over 6, because there are 6 complete waves in there. So the wavelength is that. take h divided by that number, just like you see up here. So hey, that's what they did there, that's what they did there, and there is the momentum of the electron. The uncertainty in the momentum. Now for the uncertainty of the momentum, I'm going to use Heisenberg's uncertainty principle. Delta x delta p is greater than or equal to h over 4 pi. We're going to solve for delta p because that's what the question is asking for, and we're going to go ahead and just use an equal sign. So really, I don't really know the uncertainty momentum, but I can at least find what is the smallest uncertainty momentum, and that's what they're always going to be asking. You can't really solve for anything greater. And so if I rearrange h over 4 pi delta x, now I know I can find this electron anywhere between 0 and 2 times 10 to the negative 10th. And so delta x is going to equal 2 times 10 to the negative 10th meters. Plug that in there and just do the math, and there you go for the answer. So I believe those are the work examples in section 12.1. There are other examples later on in the chapter after 12.2, some IB type questions, and of course we have the worksheet with some of these types of problems that I'd like you to work on. I will be putting the answers up, and we'll be on Friday we'll be taking a look at some of those answers and going through them and helping you with either that or cognitive problems involving this stuff. So I hope you're doing okay on this the content. Again, teaching quantum physics is sometimes tough in person, and virtually it's sometimes a little tougher. But if you did like the video, make sure you drop a like and subscribe. Make sure you hit that bell icon. Visit our sponsor. Sponsor today is the Apple iPhone. I'm totally not looking for things on my desk. The Apple iPhone, the iPhone 10, of course, the finest of the iPhones. Don't listen to these iPhone 11 people. So go ahead to apple.com/Reynolds is a genius, and they're going to give you a special discount for my listeners. It's probably going to be pretty much what you normally pay with no discount because I'm not important in that way. But hopefully you enjoyed the video, and talk to you later. Thank you.